Hi audience, now I will give a presentation. The title of my presentation is The Factors that Influence the Fluid Flow Property in a Single Crack. These are the authors of this presentation, and my name is Boye Fu. I will give this presentation. All of the authors of this presentation are come from National University of Singapore. And this is the outline of this presentation. I have divided the presentation into 5 sections. In the first section, I will talk about the motivation of this research. In the second section, I will talk about the factors that influence the fluid flow property in a single crack. And in the third section and the fourth section, I will talk about the factors that I have mentioned in the second section. And in the last section, I will give some conclusions. Now, I will begin this presentation and to talk about the motivation of this research. As we know that the crack is distributed all over the Earth, and the crack structure is related to the earthquake, the underground water migration, and oil and gas industry, and all these things are related and influenced by the crack structure. So, to detect the crack structure is one of the problems we should solve. However, the crack is in the underground, so how to detect the structure of the crack is one of the problems we should to solve in the geophysics. So, one method to detect the crack structure is use the fluid flow property in a single crack. In general, when we make fluid inlet from one side of the crack and make the fluid outlet in the other side of the crack, the fluid flow property is controlled by the crack structures. So from the fluid flow property, maybe we can obtain the crack structure. In general, the fluid flow property include permeability and flow variation versus time, and this curve is the flow variation versus time. From these two parameters, maybe we can obtain the crack structure. However, if we want to use the fluid flow property to obtain the crack structure, we need an accurate model to model the fluid flow, and we can obtain the accurate crack structure. And to get this goal, the things we should do is to analyze the factors that influence the fluid flow property in a single crack. And this is also the motivation of this research. We want to do some analysis about the factors and to know the factors that will influence the fluid flow property. So I will go into the second section to talk about the factors that influence the fluid flow property in a single crack. And at the beginning of this section, I will do some introduction about the theory that I will use in this section. The basic theory to model the fluid flow in a single crack is the Navier-Stokes equation, like this one. And the first two terms are the inertial force, which is induced by the movement of the particle of the fluid. And the third term is the viscous force. And the last term is the external pressure field. And this kind of pressure field will motivate the movement of the fluid and induce the fluid flow. In general, the velocity of the fluid particle is very low, so the inertial force can be negated, and we can approximate the Navier-Stokes equation into this form. And this means the inertial force is 0. And if the surfaces are parallel to each other, we can assume the velocity of the fluid flow is varying only in these directions, and we can negate the velocity variation in the horizontal direction, and the Laplacian factor can be written in this form. That means we have negated the velocity variation in the horizontal direction, and we can obtain the Darcy's law, of which the permeability is related to the height of the crack, and combine these two equations, we can obtain the local cubic law. And the local cubic law is one of the basic theory to model the fluid flow in a single crack. However, when we do this kind of approximation, maybe it will induce some error. As we know that the crack surface can be determined by two kind of functions. The first one is the random function, which determines the expectation height of the crack, and the other one is the autocorrelation length function, which determines the autocorrelation length of the crack. And through these two functions, we can generate a crack with rough surface. However, the surfaces are not parallel to each other, so there are horizontal variation of the velocity, and the Laplacian factor should write in this form, and we should calculate the variation of the velocity in the horizontal direction, and maybe it will also induce some inertial force, and this kind of things will induce some error when we do approximation of the Navier-Stokes equation. The other factor that will influence the fluid flow in a single crack is the deformation of the surface of the crack. As we know that the crack is in the underground and always be loaded by pressure like these ones, and when the pressure is loaded on the crack, the area that the upper surface and the lower surface are contacting to each other will be compressed. However, the area that didn't contact with each other will also have some deformation, and it will change the height of the crack, and as a result, it will change the permeability of the crack, and it will influence the velocity of the fluid flow, and it will induce some error when we calculate the permeability of the crack. So, according to what I have said, we know that the approximation and deformation of the crack will all induce some error when we calculate the permeability of a single crack. And now I will do a numerical experiment to show this kind of influence. We assume the expectation height of the lower surface is 10 micrometers, and the crack length is 100 micrometers. And we loaded pressure on the upper surface of the crack and increase this kind of pressure to induce the deformation of the lower surface. And to motivate the fluid flow, we also load stable pressure gradient in the horizontal directions, and the stable pressure gradient is at rho g. And we calculate the permeabilities of the crack. And this is the result. We use three methods to calculate the permeability. The yellow one is the result of the local cubic law, and we also considering the influence of the Poisson's effect. And I should say that in this research, the deformation influence is also called Poisson's effect. The red one and the blue one are the result calculated from Navier-Stokes equations, and for the red one, we didn't consider the influence of the Poisson's effect. For the blue one, we consider the influence of the Poisson's effect, and we can see that the result of the local cubic law is much higher than the result of the Navier-Stokes equations, and that means the local cubic law will overestimate the permeability of a single crack, and this kind of error is induced by the turbulence or the roughness of the crack. And with the increase of the pressure, there are also some difference between the red one and the blue one. And this kind of difference in the permeability is induced by the deformation of the lower surface. Although this kind of difference is not very obvious, there are some difference in the aperture distributions. And we can see because of the influence of the deformation that the aperture of the crack will be decreasing, and it will also induce some error in the flow variation versus time. And although this kind of difference is not very big, the difference is existing. So that means the approximation and the deformation of the surface will all induce error. And that means we should talk about these two factors' influence much more detailed. So I will go into the third section to talk about the influence of the turbulence. And still, at the beginning of this section, I will do a numerical experiment to show the influence of the turbulence. And the basic theory I will use is still the Navier-Stokes equation. And these are the 2D cracks that I have generated to use in the numerical experiment. And all these two cracks have the same geometries. The only difference is the pressure gradient I have loaded on the cracks. For this one, the pressure gradient is about 1% G, and according to the result, we can see that the fluid flow is laminar flow. That means the local cubic law is valid. We can use the local cubic law to model the fluid flow. And in this situation, the pressure gradient is 1G. That means the gravity of the fluid will motivate the movement of the fluid. And we can see there are influence of the turbulence. And because of the influence of the turbulence, we can see that the fluid flow out of the crack is less than the fluid in these situations. That means the turbulence will decrease the permeability of the crack. And because the surface is rough, when the flow velocity is high, the flow is not laminar flow but turbulence, and the local cubic law is broken. And that means when we do approximation of the Navier-Stokes equation to local cubic law will induce error. And we know that for a crack with rough surface, the surface can be determined by two functions. The first one is random function, which determines the expectation height of the crack, and the other is the autocorrelation functions, which determine the autocorrelation length of the surface. And all these two parameters will influence the error induced by the approximation of Navier-Stokes equation. So I will talk about these two parameters' influence on the error. And in the first, I will talk about the influence of the expectation height. And I will not research the influence of the expectation height directly, but to talk about the influence of the length of the crack. And I still compare the result of Navier-Stokes equation and local cubic law. And we maintain that the expectation height of the lower surface is about 10 micrometers. And we calculate the probabilities through Navier-Stokes equation and local cubic law. And we can see that the probability calculated from local cubic law is much larger than the probability of the Navier-Stokes equation. Only when the length is low that the results are similar to each other. However, when we look at the flow variation versus time, the difference is still very big. And from the result, we can see that the model using Navier-Stokes equation will spend much more time for the fluid to go through the crack. And when the length of the crack is long, the difference in the permeability is very obvious. And from the flow variation versus time, we still can see that the model using Navier-Stokes equation will spend much more time for the fluid to go through the crack. And that means when the turbulence influence is worse, its influence can be reflected directly by the permeability, and the turbulence will induce big difference in the permeability. And we still calculate the error induced by this kind of approximation, and from the error we know all the error is larger than 10%, and the largest error is about 100%, which means we cannot approximate the Navier-Stokes equation to local cubic law. After analyzing the influence of the length of the crack, I also analyze the influence of the autocorrelation length of the crack. And we still maintain the expectation height of the lower surface is 10 micrometers, and only change the autocorrelation length. The longest autocorrelation length is 200 micrometers, and the shortest autocorrelation length is 10 micrometers. And we calculate the probability variation versus autocorrelation length. And the difference between the result of the local cubic law and the Navier-Stokes equation is very obvious. And when we look at the error, we know all the error is larger than 10%, and the largest error is about 100%. And from the result, we also know with decrease of the autocorrelation length, the influence of the turbulence is increasing. That means with the decrease of the autocorrelation length, the error is increasing. And from the analysis set in this section, we know that the turbulence will influence the crack permeability directly, which means its influence is obvious and should be considered detailed. And with the decrease of the autocorrelation length, the influence of the turbulence is increasing. And the last one is that the roughness of the crack will induce turbulence in general, which means the Navier-Stokes equation should not be approximated to local cubic law. After the analysis in the third section, I will talk about the first section to talk about the influence of the deformation of the crack surface. And in this section, I still use these two functions to model the crack surface. So I still talk about these two parameters' influence on the error induced by the deformation of the crack. And I still talk about the influence of the length of the crack first. And we loaded pressure on the crack like this one, and use a stable pressure gradient at rho g to model the fluid flow, and use this kind of pressure to induce the deformation. And we still assume the expectation height of the lower surface is about 10 micrometers. And we calculate the permeability variation versus the length. And from the permeability variation curve, we know that the result, considering and do not considering the Poisson's effect, are similar to each other. And when the length is low, when we look at the flow variation versus time, we can see that the flow variation curve still consistent with each other. Only when the length is very long, there are some difference in the flow variation versus time. However, when we see this kind of difference, its value is less than 1% of the peak value, which means this kind of difference cannot be observed, and this also tells us the Poisson's effect can be negated. And we still calculate the error induced by the Poisson effect, and all the error is less than 2.5%, which means the Poisson's effect can be negated. After analyzing the influence of the length of the crack, and I also talk about the influence of the autocorrelation length influence, and we still maintain the expectation height of the lower surface at 10 micrometers, and change the autocorrelation length, and the longest autocorrelation length is about 200 micrometers, and the shortest autocorrelation length is 10 micrometers, and we calculate the variation of the permeability versus autocorrelation length, and all the results are consistent with each other, and the error is less than 2%, and that means the Poisson's effect is a second-order influence on the fluid flow property, which can be negated in general. So, according to the research in this presentation, I have got some conclusions. The conclusions are: the roughness of the crack will induce turbulence in general, which means the Navier-Stokes equation should not be approximated to local cubic law. And the other one is that the Poisson effect is a second-order influence on the fluid flow properties, which can be negated in general. So this is my presentation. Thanks for listening.